We are in Chapter 7, Techniques of Integration, Part 2. 7.4 is Integration of Rational Functions by Partial Fractions. We can integrate any rational function, a ratio of polynomials, by expressing it as a sum of simpler fractions, called partial fractions, which we already know how to integrate. Reversing simplifying rational expressions. So we're going to take a look at the example right below this. It says simplify the rational expression. This is an algebra problem that we are looking at, no calculus involved right now. So if you were to simplify this, since we are dealing with fractions here, we would have to find a common denominator. And so I'm going to go ahead and multiply the first fraction by x minus 2 over x minus 2. So multiplying by x minus 2 over x minus 2. And the second fraction, which we would be multiplying by x plus 3 to both the numerator and the denominator. From here, if we were to distribute the 5 to the x minus 2, we get 5x minus 10. Next, I'm going to distribute by negative 3, since there's a minus sign there, to my x plus 3 to get minus 3x minus 9, all over my common denominator, which is x plus 3, x minus 2. From here, we can simplify and combine like terms in the numerator. And doing that, we end up with 2x minus 19. And that denominator is the same. It would stay x plus 3 and x minus 2. I cannot reduce this anymore. Another way to write this would be 2x minus 19 over x squared plus x minus 6. So both of these are ways to simplify your answer here. And so what we're learning right now is called partial fractions. And some of us might have seen this back in pre-calculus. It's usually taught there. So partial fractions is the reverse of this. So we're going to be given something along the lines of what we got for our final answer here. And we're going to go backwards from this, and we're going to arrive at what we started with, that typed part up at the very beginning. So first thing is definition. A partial fraction are of the form, it's either going to be a over ax plus b to some power, we'll call it I, or, and also note that the numerator a here would be just a constant, and we'll go ahead and put that down also. Or you can have a linear numerator over a denominator that has a larger exponent, or degree larger. So we'll say a, b, lowercase a, lowercase b, lowercase c are constants. And so we're going to use long division, which was taught back in Algebra 2, to simplify a function and integrate. So if the degree in the numerator is greater than or equal to the degree in the denominator, we can use long division. So the first integral that we have here says to integrate 3t minus 2 over t plus 1 dt. The first thing to note is that the degree in the numerator is equal to the degree in the denominator. So it says to go ahead and try long division. So again, using long division, it's going to be the denominator goes into the numerator. And then also remember that if you're missing a term, we would always put like a 0 and just kind of a placeholder. What can I multiply t by to get 3t? And I would multiply that by 3. So I'm going to go ahead and write that down. And then multiplying 3 times t plus 1, I get 3t plus 3. And then we subtract. Make sure to distribute that negative sign through. And so your 3t's would zero out, and you'd have negative 2 minus 3 with a remainder of negative 5. And so I can rewrite my integral as the integral of 3, and then I have plus negative 5 over t plus 1 dt. So this right here, as we divided, we had a 3 plus negative 5 over t plus 1, and that is what we're going to be integrating. This is something we can easily integrate. Integrating 3, we end up at 3t. And then integrating 5 over t plus 1, I have minus 5 times the integral of 1 over t plus 1 dt. And I'm going to go ahead and use a u substitution here. So I'm going to let u equal t plus 1, and then du equals dt. And so I have a 3t minus 5 times the integral of 1 over u du, which is the natural log of the absolute value of u. I'm going to go and add in my plus c since I am dealing with an indefinite integral. And then I'm going to back sub in what u was. So 3t minus 5 times the natural log of t plus 1 plus c. And you might have also remembered a few things. A little note down here is that I used u substitution to show it. However, the integral of 1 over ax plus b dx is equal to 1 over a, the natural log of ax plus b plus c. So a little bit you can either remember, or you can go through that u substitution and easily arrive at the same answer. So we have another example on the next page that says evaluate the integral of x to the 4th over x minus 1 dx. And so definitely the numerator is of higher degree than the denominator. So I'm going to go ahead and divide this. So I have x minus 1 goes into x to the 4th. And I also have no x to the thirds, no x to the seconds, no x's, and no constant term. And so the next thing I'm going to ask is x times what equals x to the 4th? And you would multiply it by x to the 3rd. And so you can distribute that to the x minus 1. So x cubed times x minus 1 is going to be x to the 4th minus x cubed. And so making sure to line up your terms correctly, and then subtracting. We're going to end up with an extra x cubed left over. And I don't have any consecutive terms to pull down, so I'm going to ask myself again, x times what is x cubed? And that would be x squared. So I'm going to put plus x squared, again lining up those degrees that we have. So this is x squared, so keeping everything lined up. And then I'm going to multiply x squared times x minus 1, and I get x cubed minus x squared. And again, subtract. When I subtract, I'm going to end up with an extra x squared. I'm going to go through this again. X times x is x squared, so x squared minus x. Again, subtracting, I have an extra x left over. And then asking myself, x times 1 is x. So I'm going to have x minus 1, subtract, and I have a leftover 1. So I'm able to rewrite my original integral as the integral of, and it's x cubed plus x squared plus x plus 1 plus, and then left over we have a 1 over what we were dividing by. And then don't forget your dx. And then from here we're able to integrate, and we end up with 1/4 x to the 4th plus 1/3 x to the 3rd plus 1/2 x squared plus x. And then integrating 1 over x minus 1, if you use that formula that we wrote down here, you can still use u substitution though. But if you were to use this, it would have been 1 over 1, which is just 1, times the natural log of x minus 1, the absolute value of that. So ln the absolute value of x minus 1 plus c, our constant. So in some cases, we're able to use long division and rewrite the problem. In other cases, we're not able to do this. Case 1 says the denominator is the product of distinct linear factors. So distinct means different, and then linear would be something in the lines of ax plus b, as I wrote down in the definition below. So the first thing to do is to factor the denominator. And keep in mind that all these a's that we have are constant. And as you factor the denominator, you're going to have a1x plus b1 as one factor. Another factor is going to be a2x plus b2. And those a's are going to be constant. We're going to go ahead and use some algebra to manipulate this and find those values of those a's, those capital A's, and then we'll be able to integrate. So down below we have a definite integral. It's the integral from 0 to 1 of x minus 4 over x squared minus 5x plus 6 dx. So the first thing to note is that the numerator is actually degrees smaller than the denominator. So long division won't work on this type of problem like it did on the other two examples. So for this one, I'm going to go ahead and, like it says up above, is factor the denominator. So this is going to be the integral from 0 to 1 of x minus 4 over, and it factors as x minus 3 and x minus 2. Then dx. And so what we're going to do is rewrite this as two fractions. So we have the integral from 0 to 1 of, and like I have up above in case 1 definition, I'm going to rewrite this as a over x minus 3 plus, and instead of saying a sub 1, a sub 2, which you definitely can, I'm going to just use capital A and capital B in the numerator, and over x minus 2, and then dx. So the next thing I'm going to do is just look at the fraction part, the integrand, what we have written. And so we have that x minus 4 over x minus 3, x minus 2 can be rewritten in a way such that I have a constant value a over x minus 3 plus a constant value b over x minus 2. And this is just like that first example that we did, but again, going backwards from it. And so in order to find these, easiest thing to do is to get rid of the fact that this is a rational equation. And I'm going to multiply both sides by the denominator. So multiply by x minus 3, x minus 2. And so I'm going to end up with x minus 4 equals, and then I'm going to get a times x minus 2 plus b times x minus 3. From here, I can distribute my a and my b, and I get ax minus 2a plus bx minus 3b. And I'm going to group these, and I notice that certain terms all have an x or the variable with them, and certain ones are just constants. So there is no variable in those terms. Remember, a and b are just constants. And so I can see that I have 1x, or just x, is equal to, and it's ax plus bx. So I'm going to go ahead and say just a plus bx. And then I also see that I have negative 4, my constant term, would have to equal the constant term on the other side, which is negative 2a minus 3b. So again, since it's an equation, the left and the right sides need to be equal. They need to be the same. And so my variable part on the left side would have to equal the variable part on the right side. And likewise, my constant part on the left side would have to equal the constant part on the right side. So from here, we actually end up with, if you divide both sides by x on that first equation, we get, and I'm going to go ahead and write it underneath over here as 1 equals a plus b. And I have, so right now I have two equations with two unknowns, and we're actually able to solve this. So to solve this, you can use substitution. You can also use the addition method or the elimination method, whatever your teacher back in Algebra 2 would have called this. So if I were to do that, I might multiply my whole entire second equation by a 3, or you can multiply it by a 2. And so my equation now is going to become, I'm going to have negative, I'll write it down, the first equation again, negative 4 equals negative 2a minus 3b. And my second equation is now going to become 3 equals 3a plus 3b. And if I were to add these together, my b's are going to zero out. And I have negative 1 equals negative 2a plus 3a is just 1a or a. So I know that a is equal to negative 1. And then to find b, I'm just going to substitute this back into that original equation that I have up above, which was 1 equals a plus b. And so 1 equals negative 1 plus b, or b is equal to positive 2. So that allowed me to find those constants. And this allows me to rewrite my integral as the integral from 0 to 1. And instead of it being a over x minus 3, I'm going to have negative 1 over x minus 3 plus b over x minus 2, but b is 2. And then dx. And then we're able to integrate this. Again, I'm going to be instead of using the u substitution for this, I'm going to just go ahead and use that formula that we wrote down. And so we have the negative 1 times the natural log of x minus 3, the absolute value of it, plus 2 times the natural log of the absolute value of x minus 2. And I'm not putting a plus c since we are evaluating this from 0 to 1. It's a definite integral. So evaluating from 0 to 1. First thing I'm going to do is substitute in 1. So I get negative ln of 1 minus 3, it would be negative 2, plus 2 times the natural log of 1 minus 2 is negative 1, minus, and then I'm going to substitute in 0, so I have negative ln of absolute value of negative 3, plus 2 ln of absolute value of negative 2. From here, I'm just going to simplify this a little bit more and then see if I can combine any terms together. So I have negative natural log of 2 plus 2 times the natural log of 1 is just going to be 0. So 2 times 0. Then I'm going to distribute my negative through also. So plus ln of 3 minus 2 ln of 2. Again, distributing through that negative. From here, I can combine my natural log of 2's. And so I have ln of 3 minus 3 ln of 2. And so this would be a perfect answer. You will notice that sometimes they simplify logarithms by using some of the properties. So an equivalent way to write your answer, they could write it as ln of 3 minus ln of 2 to the third power, which would be the same thing as ln of 3 minus ln of 8. And you can combine logs together when you're subtracting and rewrite this as the natural log of 3 over 8. So again, this is equivalent to what I have boxed, and either one is appropriate for this class. If you ever have any questions about an answer and if it's equivalent to the one in the back of the book, make sure to ask. So I'm going to go ahead and circle this next example, and we'll work on this one together in class. Then we have case 2. Case 2 says the denominator is a product of linear factors and then some are repeated. And so this would be like x minus 2 in parentheses, so quantity squared or quantity cubed, so it repeats. So suppose that the first linear factor is repeated k times. And so I rewrote it as r of x over q of x equals a1 over a1x plus b1 plus, and then notice in the denominator, because it's repeated, it's now squared. And then it dot 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 through the same denominator but to the kth power. So I wrote down an example next to that. That says, for example, if you had x plus 1 over x times x plus 1 to the third power, since the x just occurs once, it's going to be a over x. But since that factor of x plus 1 to the third is repeating 3 times, I'm going to have to write it 3 times. So the first time is going to be b over x plus 1. The next one's going to be c over x plus 1 squared. and the next one's going to be d over x plus 1 to the third. Again, this is this idea of partial fractions and working backwards, just like what we discussed in that first example. The example right below says evaluate the integral of x squared plus 1 over x minus 3 x minus 2 squared dx. So first of all, in the denominator, I have x minus 3 times x minus 2 squared, and that would work out to being with the largest degree of x cubed. And so you'll notice that the degree in the numerator is smaller than the degree in the denominator, so that long division is not applicable for this problem. So I'm going to rewrite this like what we did in case 1 and case 2. And so it's already factored for me, which is really great. And so this will be the integral of a over x minus 3, since that only occurs once, plus b over x minus 2, plus c over x minus 2 squared, since it occurs a second time, and then dx. And so from here, I need to find out what a, b, and c are going to be. And so again, since these two integrals that I have written here, the integrands are equal to one another, I'm going to rewrite it as x squared plus 1 over x minus 3 times x minus 2 squared is equal to a over x minus 3 plus b over x minus 2 plus c over x minus 2 squared. And I'm going to multiply both sides by that common denominator that they have, which is x minus 3, x minus 2 squared. When I do this, we are going to end up with x squared plus 1 equals a times x minus 2 squared plus b times x minus 3, x minus 2 plus c times x minus 3. From here, we can multiply this whole entire thing out. It is going to be rather messy and do exactly what we did in the previous example. Another method to use, this is another method and it would have worked on the last ones too, is to pick a value for x. And so I'm going to say, let's just let x equal positive 2. Why would I pick positive 2 for this problem? What's nice with picking positive 2 is that it's going to zero out certain terms. So I'm going to end up with x squared plus 1 is going to be 2 squared plus 1 would be 5 equals a times 0 plus b times 0, since 2 minus 2 is 0, plus c times 2 minus 3 is negative 1. And so this is going to mean that c is equal to negative 5. Another value to select would be x is equal to 3. So I'm going to let x equals 3. And when I select x is equal to 3, I'm going to end up with 3 squared plus 1, which is 10, equals, and then I have a, and then it's going to be times 3 minus 2, which is 1. 1 squared is just 1. And then b times 0 plus c times 0. So I now know that a is equal to 10. You can select anything you would like for x. If you want to do this again, we still need to arrive at b. So some students will select, x is 0. I'm going to show you another way to kind of think about this. And I'm going to go ahead and look at, since I'm trying to find b, I notice b is definitely going to have an x squared with it, along with some x's and along with some constants. But I just need to be able to determine that. So I'm going to look at the x squared terms, just like what we did on the last one. But I don't want to multiply the whole thing out. I noticed that I would have a times, and if I multiplied x minus 2 times x minus 2, again, only worried about that x squared terms, I will have an ax squared. And then the next term, I have b times x minus 3, x minus 2. But again, since I'm only concerned with that x squared term, I have bx squared. Again, you have different ways to determine what b is. This is one method by looking at just those x squared terms. I would not have c in this problem at all because that last term is just c times x minus 3, so it doesn't even have an x squared term. Another method to do, like I said, would be allowing x equals some different values. Some students will try to plug in 0 and kind of simplify it through that and plug in c is -5 and a is 10, and they can work that out and arrive at the answer for b. So looking at this, if I divide all my terms by x squared, I end up with 1 equals a plus b. And I know that a is equal to 10. So b is going to be equal to -9. So my equation, my integral that I have up here, is going to simplify now to the integral of a over x minus 3, where a is 10, plus b, which is -9 over x minus 2, plus c over x minus 2 squared, which is -5 over x minus 2 squared dx. And then integrating each of these, the first two look very similar to what we've dealt with before. So I'd have 10 times the natural log of the absolute value of x minus 3 minus 9 times the natural log of the absolute value of x minus 2. And then I have a minus 5 times, I'm going to rewrite just the integral of 1 over x minus 2 squared dx. And so for this problem, it doesn't work out like the others. I am going to have to use the u substitution. So I'm going to let u equal x minus 2. So du would be dx. So then our integral is now going to become -5 times the integral of 1 over u squared du. Or to integrate it easily, I'm going to say -5, the integral of u to the -2 du. So integrating this, we're going to end up with -5 times u to the -1st times -1, which would make this a +5. And then back subbing in, we're going to have 5 times, and then u we defined as x minus 2 to the -1st. So piecing together what we had from up above with integrating those first two terms, we have 10 times the natural log of the absolute value of x minus 3 minus 9 times ln of the absolute value of x minus 2. And then that last term that we integrated was plus 5 over x minus 2 to the +1, or just x minus 2. And then also, since we are dealing with an indefinite integral, do not forget your plus c. So this would be our final answer. The next example I'm going to circle, and we will look at that one together in class, but do note that there is a repeating factor in the denominator also for this example. Case 3 says the denominator contains irreducible quadratic factors, none of which repeat. So irreducible means that we're not able to factor them, and none of them are repeating, so we're not going to have the quantity squared. So for example, we would have rx over qx, and since we're dealing with quadratic factors, the numerator is going to be 1 degree less, so it would be linear. And we would have all those different factors in the denominator, and again, ax plus b, depending on how many terms you have for that. Next to that, I put down an example. So it says 2x plus 5 over x plus 2, which is linear, times x squared plus 1, which is quadratic and does not factor, and also 3x squared plus 2, which is also quadratic and does not factor. Both of those are irreducible. And so I would rewrite this as, and since x plus 2 is linear, the numerator would just be a, just that constant 1 degree less. But the next one, which is the denominator, the next factor is x squared plus 1, which is an irreducible quadratic factor. It's going to have a linear factor up above, so that would be bx plus c. And then again, same thing with 3x squared plus 2, that is irreducible and it's quadratic, so the numerator would be dx plus e. A note down here to remember, very important, very useful for this section, is going to be that the integral of 1 over x squared plus a squared dx is going to be equal to 1 over a tangent inverse of x over a plus c. So we have an example right below this. that says evaluate the integral of 10 over x minus 1 times x squared plus 9 dx. So first thing to note is that your denominator is factored already. We have a linear factor, and then we also have an irreducible quadratic factor since x squared plus 9 cannot factor any farther. And so this would be able to be rewritten as the integral of, and we would have, since x minus 1 is linear, we would have just a over x minus 1 plus, and then since our second factor is quadratic, we're going to have bx plus c, in that numerator a linear factor, then dx. And so now we have to determine what a, b, and c are. So again, just like how we've done in the previous problems, I'm going to go ahead and write down what my original quadratic expression was, that integrand, and then also rewriting the right side using that partial fraction idea. So we have a over x minus 1 plus bx plus c over x squared plus 9. And then I would multiply both terms by that common denominator, which is x minus 1 x squared plus 9. We get 10 equals a times x squared plus 9 plus bx plus c times x minus 1. We've talked about many different techniques in order to solve this system, but we do need to figure out a, b, and c. And so I'm going to go ahead and use a method that we talked about, and I'm going to just say let's let x equal 1. And again, that would cancel out that second factor there. When I do this, I get 10 equals a times 1 squared plus 9 would be 10, plus, and then 1 minus 1 in that second term would be 0. So we get a is equal to 1. Next thing I can do is, I'm kind of stuck with, we did this before where we would let x equal another value, and I'm stuck with the fact that I won't be able to substitute in 3 or negative 3 to cancel out that other term because it would never sum to 0. So I'm going to select another value for x just to see if I can get another one of these constants that we have. I'm just going to say let's let x equal 0. That's usually a nice one to select. And so if I do this, I get 10 equals, and then 0 squared plus 9 is 9, so 9a, plus now since x is 0, bx would be 0 also. So I would just end up with c times, and then 0 minus 1 would be negative 1. So I'm going to go ahead and just say plus, we'll say negative c. And we know a is equal to 1, so I get 10 is equal to 9 minus c. And so solving this, we would get c is equal to negative 1. So now we just need to determine what b is. And so I noticed that my b term would end up with an x squared if I were to multiply everything out. And so looking at my x squared terms, I noticed that I would have an ax squared and then also a bx squared when I multiply those. My left side though has no x squared values, it's just a constant, it's just 10. So that means that my left hand side would have 0x squared, since there isn't any of that term, equals ax squared plus bx squared. And again, I'm just looking at those terms that have an x squared in them on the left and the right side. Since they do have a variable of x squared, the left side and the right side do need to be equal to one another. We know that dividing everything through by x squared, we get a plus b is equal to 0. And we do know that a is equal to 1. So from here, we get b is equal to negative 1. So back up at the top, we're going to be able to rewrite our integral as a, which is 1 over x minus 1, plus bx plus c. And b is negative x plus c, or minus 1, all over x squared plus 9 dx. The first fraction that we have is just going to be able to be written as the natural log of the absolute value of x minus 1. And then I'm going to separate, since I have negative x minus 1, I'm just going to separate those over the same denominator. So I'd have the integral of negative x over x squared plus 9 dx plus negative 1 over the integral of x squared plus 9 dx. So just separating those and the second term and rewriting them as two different fractions. And I noticed that, and I'll underline it, the last integral that we have would be, I'd be able to use that formula that we talked about right up above where it says remember, in expressing it as tangent inverse. And so we'll do that. And then that middle integral that we have, I do need to use u substitution on this one. So I'm going to let u equal x squared plus 9. So then du would equal 2x dx. And so this middle one right here would then be the integral of, and I'm going to go ahead and put that negative out in front. That was with the negative x. And then I'd have a negative 1/2 also as I use my u substitution. And I'm going to end up with 1 over u du. And when you integrate this, you would have negative 1/2 ln of the absolute value of u. And so my first term, kind of putting this all together from up above, was the natural log of the absolute value of x minus 1. My second term is going to be minus 1/2 ln of u, but I'm going to back sub in what u was, and u is x squared plus 9. You do not need to put the absolute value line since x squared plus 9 is always positive. So x squared plus 9, it's redundant if you do put it. And then the last one that we have is going to be negative, since I do have that negative 1 out in front. And it's 1 over x squared plus 9, which again, looking up above, I'll circle it up here. One of those ones that we need to know. It's very helpful. If you don't know it, it's going to really hurt you in the next exam. And for this, we're going to end up with 1 over, and it's going to be a squared, which would be 3 squared, so 1 over 3. Tangent inverse of, and it's x over a, so x over 3. And then don't forget your plus c. And that would be your final answer. On the next page, we have case 4. I rewrote our integral of 1 over x squared plus a squared again for us, so we have it there to look at. And then case 4 says the denominator contains a repeated irreducible quadratic factor. So this time it's still irreducible quadratic factor, but it's repeating. So in the example down below, you'll see the x squared plus 1, which is irreducible and quadratic, and it's repeating because it's quantity squared. And so for this method, for case 4, we're going to be using the methods that we discussed in case 2 and case 3. So the example says to evaluate the integral of x squared plus x plus 1 all over x squared plus 1 squared. And so for this, I'm going to think a little outside the box. I'm going to rewrite this a little bit differently. Rewrite it as x squared plus 1, which all I did was take these two terms and group them together, over x squared plus 1 squared dx plus what I left over with, and that's just the integral of x over x squared plus 1 squared dx. So with thinking outside of the box here, I noticed that when I group together some of these terms, one of my x squareds plus 1s would reduce out with the 1 in the denominator. And so now I'm going to have the integral of 1 over x squared plus 1 dx plus, and then to deal with that second integral, I'm going to let u equal x squared plus 1, because when I take the derivative of this, I notice that I get my numerator, which is what we would notice for u substitution. And so this is going to be plus 1/2 times the integral of 1 over u squared du, with using that u substitution. And so with integrating the first term, I would have, it's 1 over a. In this case, a is just 1. So 1 over 1 is just 1. And then tangent inverse of x over a. So x over 1 is just x. Plus, and then for the second integral, I'm going to go ahead and rewrite it as 1/2 the integral of u to the negative 2 du. So integrating the second one, I get 1/2 times negative u to the negative first plus c. I need to go ahead and back sub in. I'm also going to flip and put the u in the denominator. So we have minus 1 over 2, and it should be u, but u is the same thing as defined way over here as x squared plus 1. And then we also have our plus c, since we are dealing with an indefinite integral. So right below it says rationalizing substitution. Some non-rational functions can be changed into rational functions by means of appropriate substitutions. So the example right below says make a substitution to express the integrand as a rational function and then evaluate the integral. So the integral that we have is dx over 2 times the square root of x plus 3 plus x. And so from this I need to make a substitution. So I'm going to go ahead and let u equal the square root of x plus 3. And so when I do this, I notice that since I'd have an extra x in the denominator there, if I square both sides, I notice I have u squared equals x plus 3, or that x is equal to u squared minus 3. And so differentiating, and you can differentiate any of these three parts. I'm going to pick the middle one to differentiate. I'd have 2u du is equal to derivative of the right side, which is be dx, 1 dx. And so my integral that I have, and I'll go ahead and rewrite my original integral, is the integral of dx over 2 times the square root of x plus 3 plus x. And so we have the integral of, and dx is going to be 2u du. And then the denominator we have 2 times the square root of x plus 3. And that is just equal to u. Plus, and then x, since we have that, x is equal to u squared minus 3. So from here, I can go ahead and reorder my denominator so you can see that it is similar to what we've been doing before. I can pull the 2 out in front also, but we have u du over u squared plus 2u minus 3. And this does factor, so we have u du. I also want to note really quick that long division isn't going to work because our degree in our numerator is less than the degree in the denominator. And u squared plus 2u minus 3 factors to u plus 3, u minus 1. And from here, I know that I can separate this. And so I have u over u plus 3, u minus 1. And they're both linear factors, so I know that this would be, and they don't repeat, as a over u plus 3 plus b over u minus 1. And then multiplying both sides by that common denominator that they have, which is u plus 3, u minus 1. We have u equals a times u minus 1 plus b times u plus 3. And so we can definitely look at these different ways. If I were to let u equal 1, this means that my left side would be 1 equals, to have 1 minus 1, which is 0, and then b times 1 plus 3, it would be 4, so b is equal to 1/4. I would also like to let u equal negative 3 to 0 at that second term. if u is equal to negative 3, I have negative 3 equals a times negative 3 minus 1 is negative 4 plus 0, since negative 3 plus 3 is 0. And so I get a is equal to 3 over 4. So I have b and I have a. I want you to note that these are not nice whole numbers like we've been dealing with before. And so, but it works exactly the same way. So from here we have a 2 out in front. And it's going to be the integral of, and it's going to become a over u plus 3. It's written over here. So we have a, which is 3/4 over u plus 3, plus b, which is 1/4 over u minus 1 du. And so from here you can pull out 1/4, and when I do that, 2 times 1/4 would be 1/2. The integral, and now this is going to become 3 over u plus 3 plus 1 over u minus 1 du. So with integrating, we have a 1/2 out in front. Integrating the first term, we have 3 times the natural log of the absolute value of u plus 3 plus 1 times the natural log of the absolute value of u minus 1, and then plus c, since it's an indefinite integral. You can simplify by just distributing that 1/2, or you can leave it as it is, but we'll say 3 over 2 natural log of u plus 3, the absolute value of that, plus the natural log of the absolute value of u minus 1, plus c. And that would be our final answer.